In this video, we introduce polynomial rings. This comes from a later chapter in the textbook, but I prefer to bring the material slightly earlier in the course for two reasons. One, because they allow us to discuss other examples of rings, and then as we go on, ring homomorphisms and ideals. And the other reason is because we usually run out of time long before we reach that chapter. And then the third reason is because these things are interesting and because we study a lot of polynomials in lower level courses. So otherwise you're stuck with just integers. So it's good to have more examples of rings. Alright, in this video we're going to introduce a new type of ring called a polynomial ring. So we're going to let R be a commutative ring with a unit, 1. And the polynomial ring is going to be the set of polynomials whose coefficients are elements of your ring R. So note here that x is a placeholder, so it's an indeterminate. In particular, when we're discussing polynomial rings, we are not thinking of x as taking a specific value. So we're not thinking of this as an actual function. We're just thinking of it as just a sum of symbols like this. There's a valid reason for that I might state at some point. It comes from the fact that if for certain types of rings you can have polynomials that are distinct that actually define the exact same function, which is kind of weird. But anyhow, throughout we're usually going to write p of x as sum of powers of x, q of x as sums of power of x. We're going to use q sub I and p sub I to denote the coefficients. Note, whenever I do such a thing, that's implying that the highest degree coefficient is non-zero. And so once you have these two polynomials, you define their sum as follows. The constant term is the sum of the constant terms, the linear term is the sum of the linear terms, and so on and so forth, all the way up to the highest degree term. Note here, since n and m could have different degrees, I'm going to say L is whatever the higher degree is. Of course, this creates a bit of a conflict because if they have different degrees, you run out of terms in one of the two polynomials. So we say one of these sequences becomes 0 after you go past the degree. And then it turns out there's another formula for multiplication. It's given by this formula. We know that the product of two polynomials should have degree n plus m. And it turns out the coefficient of x to the I is given by this formula. So you sum as k goes from 0 to I, p sub k times q sub I minus k. To see the motivation behind where that product formula came from, the idea is assuming that you had a ring of polynomials, or you wanted to turn polynomials into a ring. How should you define the multiplication? Well, here's a quadratic times a cubic. By left distributivity, this quadratic should expand like this. So you have p0 times the second polynomial, p1x times the second polynomial, and so on. By right distributivity, you should be able to distribute some more and get this expression. So p0 distributes all the way through to get this first line. p1x distributes through. Notice by commutativity, I'm moving the x all the way to the right. And notice x times x is x squared, x times x squared is x cubed, and so on. And then I'm shifting everything over so the powers of x and x squared are all in the same column. So then finally I can group the terms involving x together and factor out that common factor of x. Terms involving x squared I can group together and factor out the common factor of x squared, and so on. And when I do this, I look and I see what's the coefficient of x. It's the sum of all the ways to write 1 as a sum of two integers, p0 plus q1, P1 plus Q0. So 0, 1, and 1, 0. How many ways can you write 2 as a sum of two non-negative integers? 0, 2, 1, 1, 2, 0. Similarly, 3, you have 0, 3, 1, 2, 2, 1. And then the next one would be 3, 0, but since there is no cubic term for P3, that part is 0. Note again, this is our convention that a coefficient is 0 when you go past the degree of your polynomial. So for instance, working in Z mod 2Z, here's two polynomials. Let's try to add them. The rule, of course, is that you're supposed to add coefficients of like powers. The coefficient of x squared in the first one is 1. In the second polynomial, it's 0. The coefficient of x in the first polynomial is 0. In the second polynomial, it's 1. The coefficient of 1, the constant term in both polynomials is 1. If you're working mod Z2, the coefficient of, you get 1 plus 1 is 2, but 2 mod 2 is 0. So that's the sum here. How about this product? Well, I mean, you could always FOIL when it's something as small as this one, but let's use my formula anyhow. How many ways can you get x cubed? Well, you have to multiply an x squared times an x term. So there's just 1 times 1. How many ways could you have gotten x squared? Well, you can get it from the x squared, or you can get, well, that's the only way in this case. How many ways can you get x? Turns out only from taking an x over here and a 1 here. And finally, there's only one way to get the constant term. So this is an example of a product. Oddly enough, like I said, there's a reason we look at this as an abstract polynomial. If you decide to look at this as a function, let's call this result r of x for now. R of 0 is 1, and r of 1 is 0. But you would discover that that's the exact same function values you would get from x plus 1. So as functions, these two polynomials would be considered the same, which is just weird. So that's why when we're talking about polynomial rings, you make the insistence that x is just an indeterminate and that we're not viewing the polynomials as functions, because once you start discussing them as functions, you have to make other identifications, and a lot of algebra starts to break down. So this is just a formal sum of constants times powers of x. Alright, so one thing I want to prove is that this set is in fact a commutative ring. That should be somewhat clear, but it's going to be a bit of a messy proof. I mean, it's partly clear that it should be a ring because we kind of defined multiplication on purpose so that it'd be distributive. But let's do the proof. There's multiple ways to write down the proof. You could actually write it down with the summations and the powers of x using the standard way of expressing polynomials, but that starts to get very messy to write down. So I'm going to do something slightly different. I'm going to use this subscript notation. P of x sub I is the ith coefficient in the polynomial. So this notation will allow us to just look at individual coefficients in a polynomial instead of the entire polynomial at once. And so first you have to show that you have an abelian group under addition. One way to show that, two polynomials are equal if they have the exact same coefficients. So I'm just going to look at an individual coefficient in this triple sum. this parenthesization and show you get the same thing regardless of where you put the parentheses. So let's do that. What is the ith coefficient of this polynomial? Well, by definition of the sum, the fact we're using here, if you go back and look at how we defined the sum of the two polynomials, the ith coefficient was just the sum of the ith coefficients. So you get Ri plus the ith coefficient of these two polynomials. But what's that? It's the sum of the ith coefficients. These are all entries in a ring. Addition in the ring is associative, so I can move the parentheses over. Now I can unwind and realize that this latter sum inside this set of parentheses is the ith coefficient of q of x plus r of x. Finally, the sum of ith coefficients is the ith coefficient of this triple sum. So we see that these two polynomials have the same ith coefficient. I was arbitrary, so they're actually the same polynomial. Note here that if I want to make this a fully formal proof, I should be a little more careful and specify that I is a positive integer. That's at most the maximum degree of the three polynomials, and specify to the reader that we're still using the convention where p sub I, q sub I, or r sub I is equal to 0 when I is bigger than the degree of the corresponding polynomial. Of course, we still have to show that we have other properties, so we need commutativity. If you take the ith coefficient of the sum of p of x and q of x, that's p sub I plus q sub I. R is commutative under addition, so you can swap these two numbers or elements. And then you have the ith coefficient of the sum of the polynomials in reverse order. Similarly, what is the identity element? It's the zero polynomial, the one where the constant term is 0 and everything else is 0 as well. How do you see that? Well, take the ith coefficient of this sum. It's just pi plus 0. That's just pi. Well, that's just the ith coefficient of p. So you do actually have that this is equal to the original polynomial. Similarly, what is the additive inverse? Well, we've discussed this before. If you have a ring with a unit, or you think you have a ring with a unit, then it's clear that -1 times r better be the additive inverse. So let's check that. The ith coefficient of this sum has to be pi plus -1 times pi. Well, -1 times pi is negative pi, because those are elements of r. And pi minus pi is 0. So the sum of these, the ith coefficient of this sum of polynomials is 0 for all I. That was the definition of our identity polynomial, or 0 polynomial. So -1 times px is the additive inverse. So we managed to show that we have an abelian group because we showed addition is associative, commutative. We figured out that the identity or the additive identity is called the 0 polynomial, and we figured out that the additive inverse just corresponds to negating all the coefficients in your polynomial. Of course, rings have a multiplication operation. So one of the advantages of using the subscript so far has been that we've gotten to avoid summation symbols. We can't do that anymore. Now I say the advantage is that I get to reduce the number of summation symbols. This is the double summation is the worst we have to deal with. So, oh, I forgot to write the word associative under multiplication here. So let's multiply three polynomials. Let's look at what is the ith coefficient. Well, what is our formula for it? Is the summation as k goes from 0 up to I, the kth coefficient of the first polynomial, which is this product, times the k minus ith coefficient of the second polynomial. Well, what's the kth coefficient of this product? Well, it's the summation j goes from 0 up to k, p sub j, q sub k minus j. Notice I have to use a different summation variable because I'm already using k. Multiplication distributes over addition, so I can bring this inside, and I have this double summation of pj, qk minus j, rk minus j. Now you can do a substitution where I decide to set a equal to j, b equal to k minus j, and c equal to k minus I. Why would you do such a thing? Well, because these formulas are messy, and wait, there's a bit of a mistake here, isn't there? Those should be I minus j's, or I minus k's. There we go. It's recognizing that what this is doing is it's taking, what happens when you add j, k minus j, and I minus k, you get I. What is this double summation really doing? It's summing over all ways to write I as a sum of three non-negative integers. It doesn't matter if you call those non-negative integers j, k minus j, and I minus k, or a, b, c. So this is something that is worth pointing out. An alternative definition to this product formula is this one. Summation over all ways to write k as a sum of two non-negative integers, p sub a, q sub b. So what's the advantage of this formula? Well, if you ever have to multiply three polynomials and you want to figure out what the coefficient of x to the fifth is, this gives you a shortcut for how to figure that out. Don't multiply all three polynomials, just figure out all ways to write 5 as a sum of three integers and multiply only those corresponding coefficients. Of course, we're not done yet. It turns out if you do the product the other direction, the same result happens. Therefore, you have associativity. Let's actually check that. The ith coefficient of the second product, the ith coefficient of this product is the summation k goes from 0 of I, p sub k times the k minus ith coefficient of qx times rx. What is the k minus ith coefficient over here? It's the summation j goes from 0 to k minus I, q sub j, r sub k minus I minus j. Multiplication distributes again, and you get this double sum that looks nothing like the previous double sum, because the variables are in the wrong, or these subscripts look completely different. But when you do the same idea, you realize, what are you really doing? You're summing over all ways to write ki as a sum of three integers. Again, I made that same stupid mistake. Boy, I feel silly today. You can do the same substitution, and then you see that you're summing over the same result. The only difference between the two summations is the order in which you're adding up the terms. And then we still need to show that you have distributivity and commutativity. So here's commutativity. If I compute the ith coefficient of the product of two polynomials, my shortcut formula is that it's the summation over all ways to write a plus b equals I. The eighth coefficient of the first polynomial plus the bth coefficient of the second polynomial. Multiplication is commutative in R, so I can rewrite the order here. I could also rewrite the index of summation without a problem, and then I see that I'm looking at the ith coefficient of the product of polynomials in the other direction. So multiplication of polynomials is commutative. This is one of those things you learn as a mathematician, that sometimes having two different ways to write down the same formula can be beneficial for proofs. This way of writing down the formula is a lot easier to work with for this type of proof, even if in actual practical calculations the other formula is the one that's easier to get a computer to work with. Finally, we have distributivity. Note, because I proved commutativity first, I only have to do one of the distributive laws, because we showed the other one follows for free. That's nice. Thank goodness, because I don't think we want to suffer more than we have to. So let's take three polynomials, add the second two polynomials, and multiply by the first. Compute the ith coefficient. What is the ith coefficient? Well, it's this summation of the kth coefficient of the first polynomial times the I minus kth coefficient of the second polynomial. But of course, that's just the sum of the corresponding I minus kth coefficients of Q and R. Multiplication distributes in R, so I can separate out the pKs like that. Then it looks like I'm adding a pile of two sums, binomials. I can actually separate that like this, because I'm working with an abelian group, so that's perfectly fine. So I could separate this summation as follows. In fact, I should make sure to put the parentheses here to make sure it's clear that what you are doing is you are summing this term up I times. Or you're summing this first term up I times and the second term up I times. And then adding the result together. But because you're working with an abelian group under addition, these two results are the same. Alright. This result is the ith coefficient in the product of P and Q, and this summation is the ith coefficient of the product of P and R. So congratulations, you do have distributivity. And if students want, I can try to find a written proof from some online textbook, because I don't remember if our textbook actually proves it. It proves this result in a later section, or it states this result in a later section, but usually textbooks try to skip this proof because it's kind of messy. So one last fact. If your ring of coefficients is an integral domain, then so is your polynomial ring. So in modern algebra 2, you prove a lot of facts about polynomial rings, and a lot of them are based on assumptions on what the coefficients ring has as its properties. This part is actually not too hard to prove. Suppose you have two polynomials that are not zero. If you write them out, then their leading coefficients cannot be zero. And if you expand the product and you look at its leading term is x to the n plus m, and the leading coefficient is pn times qm. But since you're working in an integral domain and these two leading terms are non-zero, their product is non-zero as well. And so congratulations, one of the coefficients is definitely not zero, and so the product cannot be the zero polynomial.